الآن يمكنكم المشاركة في مبادرة الأيام الرقمية تحت شعار انطلق بقوة مع جوجل، والتي يتناول فيها خبراء جوجل عناوين جديدة أسبوعيا مثل السحابيات، مهارات من جوجل، أندرويد، فلتر، ذكاء الآلة، فاير بيس، ديزاين ثينكينج، مقسمة إلى دورات وورشات عمل يومية بالإضافة إلى مسابقات أسبوعية. شاهد الأيام الرقمية مباشرة على اليوتيوب وشارك رأيك وأسئلتك مع خبراء جوجل، واحصل على شهادة حضور في كل محاضرة تشترك فيها. هذا وأكثر من الأحد إلى الخميس ابتداء من الساعة 9 بتوقيت دبي عبر الرابط المبين youtube.com/gdgmena.
السلام عليكم. hello everyone. صحة فطوركم ولا صحة شربتكم كما يقولوا في تونس. So welcome into this part 2 of vision transformers. So basically on the part 1 we have seen a little bit of the theoretical side of vision transformers, which is like something new and a very interesting architecture to get to know, to get familiar with it, because like in the future or in the upcoming years it's going to be the new state of the art. It is already the new state of the art, but now we are seeing like more implementations and more focus on it from the engineering and also from the research point of view. So as always, a small introduction about me. أنا Taha Rehah, expert machine learning trainer at Bamboo Geeks, and also a machine learning engineer at Decay, focusing on the health tech side. So let's start with a quick refresher before like deep in dive on the practice, because basically the part 2 is going to be about coding, about doing how to code or how to implement the vision transformer. But before this, let's start with small refresher about VIT. So as I said, VIT is the state of the art of image classification models. It's like even overcoming the CNNs or overcoming the ResNet model. It was implemented back in 2021 by a Google research team in a paper called "An image is worth 16 by 16 words: Transformers for image recognition at scale." So في البيبر هذه the Google team was introducing a new implementation of computer vision using transformers. For those who don't know what are transformers is a very well-known architecture that is implemented in NLP tasks, like in natural language processing tasks. But basically what Google did is trying to get that architecture of the transformer from the NLP and try to input images instead of inputting text or inputting words. So yeah, that's the whole idea behind the VIT. Vision transformer is based on transformers. That's obvious. And if we go back a little bit into transformers, as we said in the part 2 past month, transformers are also a new technology that was implemented in in a paper called "Attention is All You Need." Also, it was implemented by a Google research team. So in "Attention is All You Need," they implemented a new layer called the attention layer. And when we stack multiple attention layer, we do get something called transformers. So that's what we have. That's what we introduced like in the past session. Let's also now see a little bit how does the VIT works, like from a very general perspective, or from a very big point of view. Okay, so I will switch, I think, to Arabic because there are some comments to asking about traduction. الفي تي ولا الفيجن ترانسفورمر هي كما كنا نقولوا هي اركيتكتشر معروفه في الكمبيوتر فيجن، وكنا نقولوا انه الفي اي تي مبنيه على اساس بنيه معينه اسمها ترانسفورمرز. هذه بنيه من بنيات تعلم الاله ومن بنيات المودلز، والبنيه هذه تخلي ولا مركبه من عديد من اللايرز، عديد من الطبقات، واللايرز هذوكم موستلي نقولوا لهم attention layers. جوجل خدات في 2021 خدات الايدي ولا الاي دي هذه الفكره بيهايند الفيجن ترانسفورمرز بيهايند ترانسفورمرز وقالوا علاش لا في عوض انه ندخلوا تكست للموديل تاعنا راح نوليو ندخلوا ولا راح نبدلوا الشيب تاع الانبوت يولي صور في عوض انه كان اونلي تكست. سو هذه هي الفكره بيهايند الفي اي تي ولا الفكره ما وراء الفيجن ترانسفورمرز. كيفاش يخدم فيجن ترانسفورمر اكزاكتلي. سو كي يبدا عندنا صوره الصوره الحجم نتاعها ولا السايز نتاعها مثلا 128 بكسل على 128. ناخذ الصوره ونقسموها لسمول ايميجز اللي هما يسميوهم باتشز. سو ناخذ الصوره عباره كانكم if you know about convolution neural networks والا كانكم خدمتوا من قبل بالconvolution neural network تعرفوا انه في السي ان ان عندنا حاجه اسمها الفلترز هذوكم يقسموا لنا الصوره صوره اخرى ما اصغر ويخرجوا منها الفيتشر. تقريبا نفس الايديا نتاع السي ان ان في اللاير الاولاني ولا في الطبقه الاولى. ناخذ الصوره ونقسموها على صور ما اصغر وعلى لايرز ما اصغر والصور هذوما هما اللي يوليو الانبوت. نعود انه كما في السي ان ان نعرفوا انه ناخذ الصوره ككل ونعديوها از ان انبوت للكونفولوشن نتورك نتاعنا. لا في الفي اي تي راح ناخذ الصوره ونقسمها على صور ما اصغر ولا باتشز كما قلنا لهم. والباتشز هذوكم ولا الفيكتور نتاع الباتشز هذوكم هو اللي راح يكون انبوت للموديل نتاعنا. So when doing the patches when like creating the patches راح نمشيو لستيب اخرى. سو ستيب الاولانيه ولا الطبقه الاولى هي انه نحول الصوره الاصلانيه الى صور صغيره اللي هم الباتشز. الطبقه الثانيه هي الانكودينغ تاع الباتشز هذو. سو معناه الانكودينغ معناه انه نحول الفيكتورز هذاك الماتريس نحول الماتريس نتاع الفيكتورز الماتريس نتاع البيكسلز حولها الى معادله خطيه والا linear function using w times b plus w times الانبوت plus b واللي هي الفورمولا المعروفه نتاع النورال نتوركس. بعد نجيب البوزيشنز نتاع الصور ونعمل لهم انكودينغ اولسو. معناها في كل باتش كما تشوفوا لنا في الرسم. خليني نحل البوينتر. اوكي سو بيزيكلي تشوفوا لنا في الجيف هدايا انه each باتش عنده بوزيشن نتاعو. هدايا الباتش نمبر 1 بوزيشن نمبر 1 بوزيشن نمبر 2 انتل اخر باتش. الفي اي تي تقول لك ناخذ الباتش نعمل له انكودينغ ومن بعد نزيد also البوزيشن ونانكوديها زاد. معناها يمشي الباتش ويمشي معاه البوزيشن تاعو. I can't take only the patch without its position. Why? على خاطر the division of the patches like since the patches are going to since the image is going to be divided into patches the model ماهوش باش يفهم الريليشن ما بينهم. سو ما فماش حاجه ليس هناك حاجه تظهر العلاقه ما بين الباتشز. سو جات الفكره انه مع الباتش نحط معاه البوزيشن تاعو وهكا الموديل راح يعرف من بعد في الانكودر راح يفهم انه الباتش هدايا تابع البوزيشن نمبر 1 والباتش هدايا بوزيشن نمبر 2 نمبر 3 وعباره راح يركب الصوره مره اخرى في داخل الباك بوكس هذاك ولا في داخل الصندوق الاسود اللي هو اسمه ترانسفورمر انكودر. سو اعيد عندي الصوره اقسمها لصور ما اصغر ولا باتشز ما اصغر. I take the patches و I do encode them into a dimension specific dimension ومن بعد اخذ البوزيشن نتاع الباتشز البوزيشن نتاع كل باتش واضيفها للانكودينغ هذاك. بالطريقه هذه راح الموديل راح من بعد راح يكون الصوره عنده في العقل الباطني تاعو. نجم نقولوا كان عنده عقل باطني راح يكون الصوره مره اخرى وراح يفهم الصوره هذيك من شنو متكونه ومن بعد راح يخرج لي الكلاس نتاع الصوره ولا ديتكشن ما هي نتاع شنو موجود في الصوره المعينه. سو هذا هي الفي اي تي بطريقه او باخرى طريقه بعجاله معنا. الفي اي تي داخليا مكون من اساسا من حاجه اسمها ترانسفورمر كما كنت نقول هو was also introduced من عند الجوجل تيم في 2017. الترانسفورمر بيزد والا مكون also اساسا من طبقه واحده مسمات بالاتنشن. سو الاتنشن لاير ولا طبقه الاتنشن هي اهم طبقه مكونه للترانسفورمر. وبرشا طبقات من الاتنشن ولا برشا طبقات من المالتي هاد اتنشن كما فسرنا في سيشن نمبر 1. So if you are not like understanding what is transformer, what is multi-head attention, you can go back to session number 1 or to part 1 of this session. But basically بعجالة ما معناها الاتنشن انه next slide انه في عود انه نستعمل ار ان ان recurrent neural networks. راح يولي نستعمل just like الاتنشن على خاطر الار ان ان is wasting a lot of is like consuming a lot of time with also wasting a lot of data. So باستعمال الار ان ان اللي ما يعرفوش مره اخرى هو واحده من البنيات تعلم الاله اللي نستعملوها في معالجه في معالجه التكست ولا في معالجه الحروف. والار ان ان هذه كانت في وقت من الاوقات كانت هي ستيت اوف ذا ارت. اما الان وقت اللي جبنا الاتنشن تخلي القدره للموديل نتاعنا على انه يعرف معلومه عن الحرف ولا الكلمه اللي قبل من الكلمه اللي هو لازم يعمل لها تريتمنت. واوسو عنده معلومه على الكلمات من اول جمله الى هو الموديل وين واقف. سو في معالجه الحروف ولا في معالجه اللغه بيزيكلي نتعاملوا مع كلمات. وفي الكلمات نحبوا بعد كل كلمه نجموا نعملوا جنريشن ولا ريجنريشن نتاع الكلمه اللي من بعدها. سو نسحقوا معلومات على الكلمه اللي قبل، اما نوت اونلي الكلمه اللي قبل، also نسحقوا معلومات على الجمله من اولها الى اخرها. بالطريقه هذه نجم نفهم المعنى كامل والمعنى الشامل نجم نفهم المعنى الشامل للكلمه، وتخليني تسمح لي انه نعمل ريجنريشن بطريقه اسهل وبطريقه احسن. هذه فكره بيهايند ولا فكره ما وراء الاتنشن. والترانسفورمر بيزد على الفكره هذه a lot of attention layers والا العديد من الاتنشن من الطبقات من الاتنشن يعطيونا ترانسفورمر. المهم في الترانسفورمر انه نعرفوا انه عنده two parts ولا عنده two inputs، عنده انكودر وعنده ديكودر. الانكودر هو المسؤول على انه ياخذ الانبوت نتاع الجمله بطريقه عاديه والا الصوره والا مهما يكون الانبوت. والديكودر مسؤول على انه يخرج لي اوتبوت ولا يعمل جنريشن تاع اوتبوت. مثلا ناخذ اكزامبل نتاع ترجمه من اللغه العربيه للانجليش. So بالانجلش we can say like I'm going to learn. باللغه العربيه ساتعلم. So basically الموديل I'm going to learn هو الانبوت نتاع الانكودر. والديكودرز input ولا الديكودرز output also we can call it is سأتعلم، كلمة سأتعلم. So the model راح يترجم من I'm going to learn إلى كلمة سأتعلم. والمسؤول على الترجمة هو البلاك بوكس الوسطاني، أما المسؤول على الانبوت الأول هو الانكودر، والمسؤول على أنه يخرج لنا كلمة سأتعلم هو الديكودر. So فيه basically فيه طبقتان وإلا two parts والا نعم two parts مهمين ياسر اللي هما الانكودر والديكودر. Okay, now let's speak a little bit على الاتنشن لاير. ولا خلينا نشوف اسكو فما سؤال. Okay, so basically there is a question ما هي أفضل ممارسات لتحضير شهادة TensorFlow؟ طريقة للشبكة العصبية المتكررة. Okay, so basically Takaya is asking about how to prepare for TensorFlow certification. Basically TensorFlow certification is not going to ask you about RNN or about vision transformers. It is going to ask you about LSTMs and yeah, those stuff. احسن طريقه والافضل ممارسات للتحضير هي البراكتس. always practice, do a lot of practice. هنالك العديد من الريسورسز الافيلبل اونلاين كما كورسيرا، كما MIT 6S191 تاع الكسندر اميني. there is also making friends with machine learning. العديد من الريسورس الاوبن سورس مفتوحه المصدر اللي تعاونك على الاخر انك تحضر التنسورفلو سيرتيفيكيشن في شقها المتعلق بالشبكات العصبيه المتكرره والى الريكورنت neural networks. I hope I answered your question, Zakaya. So let's continue on the attention, on the introduction to the attention layer. الاتنشن لاير والا طبقه الاتنشن كما كنت نقول جات باش تعوض الار ان ان، باش تعوض الشبكات العصبيه المتكرره كما كان يسال تو تلقايا الاتنشن حاجه ما اقوى من الار ان ان. علاش؟ على خاطر كما كنت نقول هي تاخو الجمله، تاخو الجمله ككل، و it's going to pass المعلومه على الجمله ككل في كل مره I want to generate a new word ولا a new sentence. في الكيس هذه اللي تشوف الاكزامبل اللي تشوفوه قدامكم x1 x2 x3 حتى الاكس ام هما كلمات input. و x1 برايم x2 برايم x3 برايم حتى xt برايم هما الاوتبوتس ولا الجنريشن اللي راح يكون اللي راح تصير لهم جنريشن. So basically الاتنشن what is doing هي راح تعمل some calculation some variables called k و v و q اللي هم تشوفوهم الان قدامكم. مش راح ندخل في الديتيلز برشا على خاطر شفناها في البارت 1. if you another time if you want to understand more theoretically how this is happening, please go and check out part 1. But now what I'm going to tell you is that like to generate x2 prime I need to have information about x1 prime ومعها information على x1 x2 x3 حتى xm. هدايا القوة الاتنشن. so الاتنشن تعطيني معلومة على الكلمة اللي قبل مني وعلى الجملة ككل، الجملة الأصلية ككل. بالعكس في الار ان ان ناخذ جوست المعلومة على اللي قبل مني، جوست المعلومة على الاكس 1 برايم. so هدايا الفرق الرئيسي بين الار ان ان والاتنشن. في الاتنشن عندنا lot of variables اللي هما كنت نقول عليهم قبيله الكي والفي والكيو، اما ما حاجناش نفهموهم for now for practicing because like we introduced them last time. But basically there is something ولا فما حاجه اسمها self attention layer. self attention layer هو variable اخرى من الاتنشن layers والا واحد من انواع الاتنشن layers. الفرق بينه وبين الاتنشن العادي انه في self attention layer عندي only one encoder. so الانكودر والديكودر عملت لهم دمج ولا عندي one input واللي هو اسمه self attention ولا عندي زعما layer واحد واللاير هذاك اسمه self attention layer. وبعد فما نوع اخر من الاتنشن اسمه المالتي هيد سيلف اتنشن لاير، هو عكس السيلف اتنشن. سو في السيلف اتنشن مش عكس، مزيد متطور اكثر شويه من السيلف اتنشن. السيلف اتنشن قلنا عملنا عمليه دمج بين الديكودر والانكودر. في المالتي هيد سيلف اتنشن ولا عندي دمج اما multiple heads. معناها في السيلف اتنشن كان عندي only one input expecting one output. في المالتي هيد سيلف اتنشن I can take as many inputs as I want as an input or I'm going to expect like that much outputs. So that's the idea behind multi-head attention. Yes, okay, sorry. So that's multi-head self-attention layer. بعجاله وبملخص باش نتعداو الكودينج. Vision transformer based على multi-head self-attention, based على normalization, based على encoding and decoding the patches of the image. So basically that's the idea behind VIT. الباتشز اللي حكينا عليهم قبل هذه example of them. So مثلا هذه الصوره راح نقسمها على الباتشز وكل باتش راح يكون فيه 16 على 16. So هذه واحده من examples. والايمج تولي في عوض انها تكون ايمج واحده يولي عندي 16 times 16 image. So بالطريقه هذه ولاو عندي multiple images, multiple small images, but the model is going to understand which image is corresponding to the other thanks to the position embedding. اوكي سو بيزيكلي في كل باتش راح يولي فيكتور، راح نعملوا له ترسيم على شكل فيكتور. سو عندنا x1 x2 x3، في كل x عندنا باتش معين ولا صوره واحده مصغره من الصوره الاصليه. بعد ما نخرج الباتشز نعديهم على dense layer. سو لنا قاعدين نفسروا ولا here we are going to understand how technically the VIT is going to work. Another time I'm just doing a refresher, that's why I'm going so fast. But if you want another time to understand more, please check part 1. So as a refresher, after taking the input of the patches, I'm going to pass each patch to a dense layer. اللي يقول dense layer يقول neural networks يقول famous equation of W times X plus B weights و biases. اللي يقول فما dense layer يقول فما parameters يقول فما weights and biases. So بعد ما نعدي x1 على dense layer راح تصير لي generation تاع some parameters اللي هما W and B وراح يكون عندي output vector a new output vector called Z1. So بنفس الطريقة راح نعمل calculation Z2 Z3 until Zn وبالطريقة هذه راح يكون عندي like as many patches as I do have in the input اما كلهم they share the same parameters. هذه حاجة مهمة في الفيجن ترانسفورمر انه اللاير هدايا نفس W and B اللي شفناهم here. So this W and B are going to be the same for X2 to output Z2, for X3 to output Z3 until we reach Xn with Zn. So هدايا واحدة من الحاجات اللي we need to take care of while coding the VIT. اوكي بعد ما نعمل calculation تاع الفيكتورز هذوما Z1 Z2 Z3 until Zn I'm going to add the encoding of the positional vectors. So those positional vectors هما position 1 2 3 each position عندها vector معين. So مثلا الفيكتور هذا فيه 4 cases والنورون اللي فيه value هو النورون number 2 هو الcase number 2. So which means that this patch corresponds to the second position inside the image, etc etc etc. I do add this vector to this vector, then I will have a new output vector. New output vector, sorry, I will show you the vector. New output vector called Z, but Z includes the past Z plus the positional encoding. And as an example to show you the idea behind the positional encoding, you can see this picture of dog. تصوير الكلب here. You can see انه if I take الباتشز عملت لهم shuffle عملت لهم a little bit من shuffling random shuffling بدلت البوزيشن نتاع البوزيشنز نتاع كل باتش. كي بدلت البوزيشنز ولات عندي صوره اخرى جديده فيزوالمون ولا فيجوالي معناها لي انا كانسان. اما بالنسبه للموديل ستيل نفس الصوره على خاطر البيكسلز هما ما تبدلوش. اما تبدل البوزيشن تاعهم الموديل ماهوش قاعد ياخذ في عين الاعتبار البوزيشن. هذاك علاش جات الايديا انه ناخذوا البوزيشنز ونكوديهم باش حتى كان عملت شافل ولا كان صار شافل في واحده من ستيبس I'm going to understand that there is a shuffle, but I'm going to keep in mind the initial idea behind it. So yeah, that's the final model that we are going to build. So we are going to build the patch encoder, the dense layer, then another positional encoder, then add a multi-head self-attention, after it a dense layer, and keep repeat as many layers as we want, as many blocks as we want, to form something called the transformer encoder network. Okay, so by the end of the transformer encoder network, I'm going to input or to link a softmax classifier. That softmax classifier is going to tell me which class does the input belongs to. So that's the schema about what we are going to build today. You are going to take an image, divide it into patches, encode the patches, add positional embedding, input the positional embeddings to transformer encoder, expect an output, pass the output to a multi-head multi-head classifier, and then I'm done with my classification. So that's the architecture of the system that we are going to build today. Let me see if there are any questions before starting with coding. Okay, so ما هي أنواع مستويات المختلفة TensorFlow. Basically الانواع المستويات المختلفه في TensorFlow. اوكي so TensorFlow فيها more than 4 levels مش 4 levels اما 4 categories اللي هما ساعات 3 ساعات 4 ساعات 5 اللي هما الكمبيوتر فيجن اللي هما NLP اللي هما التايم سيريز واللي هما neural networks. So you need to get knowledge about the time series, about computer vision, about NLP, about neural networks. If you master those 4, you can go ahead and take the TensorFlow certificates if you are interested with it. Okay, so we have Stofa. What if the image dimensions, height and width, are not evenly divisible on 16? What would be the best approach, ignoring the remaining pixels or padding them until reaching the divided set? Okay, great question, Stufa. Thank you. Exactly. So if the image dimension is not is not divisible by 16 or by 24 or by whatever we choose as the size of the patches, we do the padding. We just pad the remaining pixels. So مثلا I divided by 16. The last patch has only I don't know, 10 pixels. I'm going to pad the others to get the 16 there. We never just put in mind that in computer vision it's preferable to not lose data but get more data. So if we ignore the pixels, it's going to be bad for the model. He's going to lose pixels. But basically, if we keep them and add some more white pixels, we call them white pixels because we are just padding with white pixels, it's going to be better. Clear? I hope I answered the Stofa and Takaya. Now we are going to go to coding. Okay. Okay, so let's code. Here's the link of the collab, the notebook. I think the moderator will share it with you on the chat. Yes, thank you. So okay, basically this collab. I'm going to zoom a little bit. Sorry. This collab is the official collab of Keras. Like I just took the official collab from Keras, and we are going to go deep dive on it step by step until we understand it. Because I believe that there is nothing better than if you want to learn something new, there is nothing better than the official documentation. So if you go to Keras, type VIT, you're going to find this official notebook written by the Keras team. It's very well explainable. So we are going to deep dive on it, ask questions, understand what they do, then by the end turn our model. So let's connect the collab. Basically, they are asking us for the very first thing to do is to install TensorFlow add-ons. TensorFlow add-ons is we can say the beta version of TensorFlow. So it contains anything that is not stable yet. It is held in TensorFlow add-ons. So you can find cyclical learning rate, you can find VIT, you can find some loss functions that they are not very popular, etc. So TensorFlow add-ons is a very good package to discover. Okay, so TensorFlow add-ons was installed using pipe. Now I'm going to import NumPy, TensorFlow, Keras, layers from TensorFlow.keras, and TensorFlow add-ons as TFA. So simply doing this. And now here we are importing the data. So in this example, they are using the CFAR 100 dataset. Who doesn't know CFAR? CFAR is one of the most popular open source datasets. It does contains multiple variations. واحدة من الفاريشنز هي CFAR 100. CFAR 100 فيها 100 class 100 class. وهنالك also CFAR 10 فيها 10 classes. So basically خليني نوريكم some of the classes. So هذوما classes 100 class موجودين في CFAR. You can find from fishes, animals, don't know, humans, vehicles, tractors, rockets, etc., etc. So CFAR contains 100 class of images. We are going to import it from Keras. It's already splitted and ready for us. So sorry. So how to implement it or how to import it? Just like by calling keras.datasets.cfar100.load data. So load data is going to return two tuples. The first tuple contains the train data, and the second one contains test data. So it's basically splitted by 2018. So 20% training and 80% testing. That's the test, and it's ready for us. We can run this. Yeah, and by the way, the size of the image, or the shape of the images, is 32 by 32 by 3, which means the images are RGB, like they are colored images, and they have 32 by 32 pixels. You can see here that the shape of the training is 15,000, and the shape of the testing is 10,000. So the total dataset contains 16,000 images, Haldane 100 class, as we said before. Okay, now always, like on the professional side, on the professional side, on the practice side, we always define the hyperparameters first. We never, not we never, but we preferably define our hyperparameters in one specific cell, then start building our model. What are the hyperparameters? The hyperparameters are the parameters that we as humans can control or have control on them. Like what? Like the learning rate value, like the batch size, like the number of epochs, number of patches here in our case on the AVIT, etc., etc. So here we are defining as starter learning rate 0.001. I'm defining also weight decay. The weight decay is the value that is one of the methods that is going to help to decay the weights or to optimize the weights. Then there is the batch size. The batch size is the number of images that they are going to be passed to the model in one single feed forward, or one single feed forward and back pass. There is also the number of epochs. So here we choose 100 epochs. And here the image size. So TensorFlow or Keras is suggesting us to resize the initial images from 32 by 32 to 72 by 72. Why? Because basically 32 is small, is a small like image. So it's preferably to scale it to a bigger image to be able to get more patches and to be able to extract more data. Then there is the patch size. The patch size is up to us. We can define a patch size of 6, of 10, of 11, 14. It's up to us. So here they choose the patch size of 6. And here they are printing, or they're calculating the number of patches. So an image, let me go back to the slides. An image like this مثلا contains 224 by 224. If I say that I'm going to divide the image by small patches, and the size of each patch is 6, which means I'm going to divide 224 by 6, then pow 2. Because like I have X and I have Y's, to give me how many patches are going to be inputted to the model, or how many patches are going to be divided from the image. Okay, so this is the number of patches. Then here there is the project dimension. Project dimension is the projection dimension is a parameter that is well known on the transformer while working on the transformer architecture. It's like the size of the vectors that I'm going to expecting the model to train on them. So here they are specifying 64. We can change it to 48. We can even scale it more to 92 or something like this. It's not a very important parameter for us for now. Here the number of heads. Remember قلنا multi-head attention and have multiple heads. Here I'm specifying how many heads I'm going to input to our multi-head self-attention layers. Okay, so those are some specific parameters for TensorFlow for the tensors or for the calculation. I'm going to introduce them more while coding. And here I'm specifying the MLP, or of the dense layers. So here I'm specifying first dense layer as 2048 and second one as 1024. So yeah, I'm specifying those as hyperparameters. I'm seeing some questions. اوكي سو تقايا another time. هل يمكننا دمج كود برنامج TensorFlow اندرويد في مشروع تطبيق فلاتر؟ اذا كان الامر كذلك في اي مجال مجالات المشروع. Okay, so you are asking about like merging TensorFlow with Flutter or with Android, which is something doable, of course. Not because like they are all Google technologies, but because those technologies do orchestrate each other. Nowadays, most applications are powered by AI, and they either use Flutter or Android as a front, and they use AI using TensorFlow. Yes, it's doable. At what step you need to develop the TensorFlow model like by its own, then develop the Flutter application by its own, then link the two parts using an API. It's like simply like as simple as that. Stofa, wouldn't the image upscaling impact the accuracy of the classifier? Okay, good question. Another time, Stofa. Exactly. Yes, it can impact the accuracy of the classifier. It won't like 100% impact it, but yeah, it can have an impact because I'm scaling, and when I'm scaling, I'm like just like shrinking the pixels. They are not. There is no padding or something like this, but I'm shrinking the pixels from 32 by 32 to 72 by 72. But it's still like holding because the images here in CFAR are mostly centered in the center and mostly are like images of objects, small objects or very well-known objects. So basically, if I resize, if I like resize on the upscaling part, it won't have that much impact. But yeah, you can skip stuff. You can skip this part. You can like not resize the image and see what's going to happen. If we have time, we are going to do it and compare the accuracies of the two models. Okay. Okay, so I took Takai is really asking the question in English. So he's asking about which folder in the project tree. Actually, not basically in a folder, unless you wanna do offline inference, like you wanna inference on your mobile device. Here you are going to need to use TensorFlow Lite. TensorFlow Lite is the version Lite of TensorFlow that is like able to do inference on very small devices like mobile phones. But basically, for the simplest way, just like link the application to an API. That's going to be better. Okay, so now let's move on to like data augmentation. Why? Because always while dealing with data, always when we say images, we say that data augmentation, because mostly computer vision datasets do overfit very quickly because the model mostly is very sure that he have seen like all the data that he needs to see. Then he's going to overfit, and this is something that we are not looking for, or we don't like to have a situation in it. That's why there is something called data augmentation. It allows us to just like generate new images from the initial or from the source images. Like I take the first image of a cat مثلا, then I flip it, I rotate it, I zoom, I rezoom, I like change the factor of the flipping, like horizontal or vertically. I change the color system, etc., etc. So that's what data augmentation is about. And here they are just like normalizing the normalization layer. Then they are resizing. Here's Tofa, you can like remove the resizing layer to see what's going to happen. So just like comment it and see what's going to be the difference. So here they are resizing, then they are doing random flip, random rotation, random zoom, and they are done. We can add as many layers as we want from data augmentation. So it's not something that's complicated. Okay, then this layer is going to be named data augmentation, and we are going to run. Okay, so there is an error, and the image size not defined. Okay, I think I commented the image size. Oh no, I didn't run this cell. Sorry. Okay, so let's rerun this. Okay, now that we have built our data or have prepared our data, pre-processed our data, now we are going to build the model. Let's go back to the slides a little bit. Now, and know the very first thing to do is to patch the image. Then after patching the image, I'm going to pass the patches to some dense layer, to one specific dense layer. I'm going to create a specific dense layer for me called MLP, just like MLP. It's a function that you give it how many hidden units you want and how many dropout you want. And it's going to call the simple keras.dense layers, give it the units, then the simple keras dot layers dot dropout, and make a dropout. So this is not something weird to do. I can remove this and add layers directly directly to the model. Okay, now we can talk about patches. Patches, I need to create patches. And thanks God, there is something in TensorFlow image module called extract patches. So I'm not supposed to code a lot of code on my own function to extract the patches. In TensorFlow, they do provide us with extract patches function, which is like a very old function that was even implemented before the VIT. But with VIT, they updated it to version number 2, and it's going to help us in the VIT a lot. So I go to tensorflow.image.extract patches. I give it the batch size of the image, like the whole bunch of images, the whole 256, because extract patches is doing parallelization, is supporting batch or bulk upload. That's why I can give it a batch size, a big whole bunch of images, and it's going to work. Then the second parameter is the sizes. So the sizes is the size of the patch. Simply, like here, the self.patch size, which is like the parameter that I'm going to pass. So patch size in our case is, I think, 6. Patch size is 6, yeah. So TensorFlow is going to divide the image to patches of 6 by 6. The strides mostly, or in all cases, is equal to size. So we always specify the stride as equal to size. Why? Because what is the stride? The stride is the amount of pixels that I'm going to stride by, or to نعمل translation by this number of pixels in the stride. Since in our case, I need to take the first 6 pixels, the first 6 by 6 pixels, and then move to the next 6 by 6. So in this case, the stride is 6 by 6. That's why here I'm applying 6 by 6. The rates, it's a personal parameter in extract patches, but it's per default 1111. Then the padding is valid. Remember, Stofa, when you asked about what happens if there is like some images that are left that are not fitting the size of the patch. Here we specify padding either equal to valid or either equal to same. If you like specify valid, which means there is no padding, so no padding is going to be applied. But if you are sure that there are some images that they are not going to fit inside the size of the patch, then specify the padding to be equal to same. Okay. Okay, then I'm going to output like the patches dimension and reshape all of this into a tensor of batch size and patch dimension. So this is my very first class. And then let's see if this is going to work or not. So here I'm going to visualize what's happening here. You can see that the new image size is 72 by 72. No more 32 by 32. You can see that the patch size is 6 by 6. And the number of patches inside the image is 144. So here I have 144 small patch, which is something huge. Not that huge, but yeah. And inside each patch there is 108 elements or 108 pixels. Okay. Yeah. So let's run another time this cell to see another image. Yeah. So you can see that this image is an image of a pepper, I think. Yeah, red chili, and it was divided by like. By 6 by 6 patches. Also, Stofa asked about rescaling. You can see the effects of rescaling here. If I do remove the rescaling, if I do go up and I do remove the rescaling, like this, I do run the data augmentation cell. Okay, then I go back to my visualization. Normally, it will change the outputs. Okay, so basically the images, sorry, here they didn't apply. Okay, so missing something. Oh yeah, they are doing resize also here. So I need to remove the resize here. The resized image. And apply this to directly the image. Okay, so yeah, basically, never mind the error, because like it's normal. I need to give it a tensor, but basically, yeah, but basically the image. This is the original image. You can see that there is no like that's blurring on all the image, but the blurring is only on the exact. On the center of the image, and you can see that the shape is 32 by 32. So yeah, there is a difference, but basically it's not something that big. So let's go back here. Let's remove the resize. Let's get back the resize and go another time back with the resize here. Okay, let's see the comment section. Ok, so basically, Taha, est-ce qu'on peut ajouter et importer des modules externes plugins ou API comme le code d'un programme Tensorflow aussi? Yes, we can add plugins, not plugins, but yeah, we can add libraries. Can add libraries to our code. Yeah, basically, we can do this. We can consume external APIs, and we can create our own API using Flask, using Django, something like this, to be able to expose the model to the real world or to our mobile application. If you are still asking about the mobile application. But yeah, basically TensorFlow is a platform. So it's not only a library, it's a platform. It's offering end-to-end tools. So you are not going basically to need external tools, but if you need them and you find them, please go ahead and use them. Okay, so Yasmin is asking, didn't get exactly what the patches are. And Stofa is answering Yasmin. Okay, great. But basically, the patches, Yasmin, are let me go back here. Oh yeah, let me go back to the slides. Okay, so you see the image. Sorry, where is the image? Yeah, you see the image here. This is the original image. The patches are, as Stofa said, they are like tiny, small images of the original image. So I'm taking the image, the original image. I'm dividing it to patches, to small patches. This little square is called patch. This one is also a patch. This one is a patch, etc., etc. So those are small patches. And this is the original image. So what's the idea behind dividing the image to small patches? Is given the model multiple inputs so he can understand the relation between the patches. What's the model is going to learn here, and what's the difference between Visual Transformer and CNN is that CNN is going to learn features region by region from the whole image using filters. But VIT is going to learn the relation between the image and is going to define features from that relation between the patches. That's why patches here are very powerful in the case of the VIT. But yeah, patches are just like the small parts of the image. I'm just dividing the initial image or the source image into patches. Clear, Yasmin? Okay, so this is another image that was divided into patches. This is the original image, and those are patches. Those patches are going to be inputted to the model. Remember the schema. After dividing the image into patches, those patches need to be inputted to a dense layer. So I need to encode or to embed the patches using the dense layer. How to do this? I'm going to create a new class called the patch encoder. What does the patch encoder do? Like simply pass the vector or the whole patch into a dense layer, into a specific dense layer. So here I'm taking the number of patches as an input. The projection input, which is like the number of the units inside the dense layer. So the dense layer here is having 64 projection dimension. Remember, 64 units, by the way, sorry. Remember here when I told you on the upper parameters that there is a parameter here called projection dimension 64. 64 is the number of or is the length of the vector that is going to be outputted after the dense layer. So I do apply a dense layer that has 64 neurons, then I'm expecting that dimension in the output. After applying the dense layer, I'm going to apply an embedding layer. An embedding layer is basically like most known, very well known in the NLP stuff. So embedding is just like coding the values into some specific dimensionality or some specific plan. We're not supposed like to understand it in this session, but we can even like remove the embedding because we can do our own embedding like just by coding it, safe coding it. But basically, TensorFlow or Keras is helping us to do this with this layer. Yes, then this is the call function. Like when I call the patch encoder, what happens? Like I'm going to go and get the positions, then add the positions to the projection, uh, to the embedding. So that's this. Those two lines, are doing this. Are embedding the patch, then add in the positional embedding. That's what exactly those two lines are doing. So I'm going to take the position here, then take the position, then like add the embedding of the patch with the embedding of the position. So this is the position embedding and projection or patch embedding. The embedding layer is only helpful with the position because I need to. The position is one number, but I need to change the size of the position to specific vector. That's why I'm using the embedding layer. Now we are done with the things that we need to build ourselves. Now we are going to build the VIT from scratch. Exactly. So how to do this? We have seen that we need one layer, one patches layer, then one dense layer or one embedding of the patch, then add the embedding to the position. After the position, I need to specify a multi-head self-attention layer, then dense layer, then multi-head another time, then another time dense, until I reach the classifier or the end of the classification. That's what I'm going to do now. So here I'm having VIT classifier as a function. So I have the input layer, which takes the input shape. I do augment the data using the layer that we created before. I do create the patches using the class اللي حكينا عليها قبل. So I give the patches, I give it the patch size and also give it the augmented images. So the augmented images are going to be divided into patches and hold it inside this tensor. So patches is a tensor here. Then I'm going to encode the patches with their positions. So I'm going to call this class. Remember this class that's like just takes the image and its position. Then it encodes the two. So I'm going to encode the patches using this this class that we just built, and I'm going to iterate into transformer layers. So transformer layers here, we said that I'm going to have 4 transformer layers in the Apple parameters. Let me go up. Yeah, so I'm going to have 8. I'm going to have 8 transformer layers, which means I'm going to have 8 multi-head self-attention plus dense layer. So 1, 2, 3, 8 times. I'm going to form my transformer encoder part. Okay, so this is this is our layers. Our layer is going to contain a normalization layer as the very first block. Then I'm going to apply a multi-head attention layer. So you remember, there is a multi-head self-attention. Why there is normalization? Because in the paper, in the official paper, they did include a normalization layer. So that's why in the code I'm adding it. But in the slides, there is no there is no normalization because it's just like a detail, technical detail. But in the code, we need to add normalization layer, then multi-head attention layer, which like the multi-head attention layer is already built inside TensorFlow, inside Keras. So I just like give it the number of heads that I want. Here in our case, 4 heads. Like I'm going to give it 4 patches. Number of heads equal the number of patches by batch. So if I divide the image into 144 patches, number of heads equal 4, which means like that in each layer, I'm going to just pass only 4 patches. So I'm going to pass only 4 by 4. Then the key dimension, which is the projection dimension, 64. Dropout, which is 0, 1 in our case. Then another time after the multi-head, I'm going to add the dense layer. So here I'm adding attention output and encoded patches واللي هو فيه images. So it's a skip connection. Here I'm not going to go deep dive into skip connection because in the official paper they did that, but they are just like inspiring from ResNet. So instead of going from bottom to top, like one layer by one layer, no, they are implementing a skip connection, which means like after calculating the first layer, I'm going to pass the output into not the next, but the after next layer. This is called like skip connection. Then مرة أخرى راح نزيد normalization layer بعده multi head or multi layer perceptron وإلا dense layer. Then مرة أخرى skip connection. So هدايا يتسمى one block, one transformer layer. So هدايا one transformer layer. I'm going to make 8 of them. So 8 transformer layers. So it's going to be a little bit huge, but yeah. Then after ending the transformer, بعدها I can do whatever I want. I can like just simply add a dense layer containing the number of classes, or add some more layers. So I can add some normalization with some flatten, with some dropout, and with also some dense layers. So this is the choice of the people on the paper. But basically we can play with this because it's up to us. Then we add the output layer واللي هو generally فيه number of classes or number of outputs. And then I do concatenate all of those layers into something called keras.model. I give it the inputs and then I give it the outputs اللي هي logits, and the output contains everything that we talked about before. So yeah, I run this. Now I'm going to experiment our model. I'm going to try it. I'm going to compile it and run it. So there is an error here. Sorry, MLP is not defined. Okay, so I did skip the run of MLP here. Yeah. So in this experiment, I'm going to use Adam W or Adam weighted decay as an optimizer. Then I'm going to use a sparse categorical cross entropy as a loss function because I have multi-class classification. And I'm going to use as a metrics the accuracy, the top 1 accuracy and the top 5 accuracy, because those ones are the metrics that has been used in the paper, in the official paper. So I'm using them and to see if like the paper, if I'm going to reach something very similar to the paper or not, or no. Then here, like just some callbacks to stop the model from training. Here, just like fitting model.fit, the one that we all know. Then here I'm going to plot the top 1 accuracy and the top 5 accuracy. It's going to take a lot of time, so I'm not going to wait for it. It's going to take a lot of time because it's going to learn from scratch. We are not doing here transfer learning. Unfortunately, as far as I know, there is no transfer learning now with VIT. There is no like pre-trained model that we can use that is implementing VIT. I think there are other models like CoatNet that they are using attention with neural networks or with CNNs, but not VIT. There is no, as far as I know, there is no transformer or there is no transfer learning for VIT. Why? Basically, because like you can see the link link on the chat of the paper. In the paper, they trained the vision transformer on a very huge dataset called GFT. GFT is a private dataset of Google. It contains 300 million images, which is like something very huge, and we are not going to reach by any by any step the accuracy that they are going to reach, Homo, because they trained it on a very huge dataset, and it's something that is not accessible by us. But with this dataset, they achieved. Yeah, here is the CFAR. Okay, so here is the CFAR 100. So they trained it on the GFT. Like they did transfer learning on CFAR after training on GFT, and they achieved 94% of accuracy, which is something very huge. But for the training, let's see the training. I think they reached 76%. I can't find the exact number, but yeah, they have reached a very interesting number. I can't find it. Okay, no worries. They have reached an interesting accuracy, but we are not going to reach it here in Colab. Specifically, our training on CFAR, and we are not doing something like very huge. But we can wait for the model to train, and then like save the H5 model and make it like retrain it or make it transfer learnable. So like we can use it on other tasks and retrain it or fine tune it to have better tasks. So we can do this by our hands. Wait for it. I think one night. It will take one night, something like this. You can see that accuracy is starting with 0.01, which is like something very low. But mostly after 100 epoch, it will reach 55%. So if you want to wait for it, just please don't like forget to activate the GPU. You need a GPU accelerator, and you can wait for the accuracy. But basically, this is the code. You can check if there is any transfer learning possibility to do with Vision Transformer, and implement it. It's going to be a lot easier and useful for like people that are going to use directly the model on something real life. Here, I'm just like trying to understand or doing some experiments. But if you want to use this on real life models, it's on real life tasks. It's preferably to do transfer learning. That's the idea. Stofa, can we use transfer learning with this type of models? If so, what layers should we freeze and what layers should be retrained or replaced? Okay, good question. Good question, Stofa. As I said, yes, we can do transfer learning. Of course, we can do transfer learning on any type of models, but if it is available or no, I don't know. Let me look. Let me look after it now. So VIT transfer learning. Basically, if there is no TensorFlow, PyTorch, papers with code, something like this here, which means that there is no available public model. But let's check very quickly on papers with code. For people who do not know papers with code, it's something that is it's a heaven on earth, because it's helps you have the code and have the paper, so you can understand on both sides. So just like type here vision transformers. مثلا yeah, there are some vision transformers. Okay. So we can take I don't know, the CCT, yeah. Okay, so here in this case they are doing image classification using vision transformer, which is like compact convolutional transformer. Not the same architecture, but yeah, it's not something like it's not something very reliable on. But yeah, to answer your question another time, what layers should we freeze and what layers should we retrain? It's up to you. It's up to you. It's up to your data. You can unfreeze 10% or you can unfreeze 100%. It's up to you. But keep in mind, the more you unfreeze, the more time it's going to take and the more memory or the more power you are going to need. So it's up to you, and it's about like what you have as resources. Are you training on your machine? Do you have GPUs? Do you have big data? Do you have less data, etc.? Okay, so basically, if there is no other questions, let me check this. Yeah, it's going up. If there are any questions, guys, please type them on the chat. Otherwise, thank you for attending the session. Thank you. See you inshallah next session in another topic. Inshallah تكون also another interesting topic, and it's going to be inshallah having more practice and having more fun. Thank you. Good night.